Today's lesson is all about gas chromatography. It's already late and still can't understand gas chromatography? Do not worry, I'm here to help you with it. So let us first start with the question, what is gas chromatography? So let's search from Google gas chromatography. So according to ChemLibreText, gas chromatography is one of the most widely used techniques for qualitative and quantitative analysis. It is a common type of chromatography used in analytical chemistry for separating and analyzing compounds that can be vaporized without decomposition. There are two types of gas chromatography. That is gas-liquid chromatography and gas-solid chromatography. Gas-liquid chromatography is based on partitioning of the analyte between a gaseous mobile phase and a liquid phase immobilized on the surface of an inert solid packing or on the walls of capillary tubing. While gas-liquid chromatography is based on a solid stationary phase in which retention of analytes occurs because of physical absorption. It permits the separation and determination of low molecular mass gases like air components, hydrogen sulfide, carbon monoxide, and nitrogen oxide.
Since we already know the meaning of gas chromatography, let's now focus ourselves to
The instruments for gas-liquid chromatography are the following: a carrier gas system. A mobile phase gas in chromatography is called carrier gas, and it must be chemically inert. Helium is the most common mobile phase. The next instrument is sample injection. It is a sample port necessary for introducing the sample at the head of the column. Motor injection techniques often employ the use of heated sample ports through which the sample can be injected and vaporized in near simultaneous fashion. A calibrated microsyringe is used to deliver a sample volume in the range of a few microliters through a rubber septum into the vaporization chamber. The next instrument is column configurations and column ovens. The thermostated oven serves to control the temperature of the column within a few tenths of a degree to conduct precise work. The columns in gas chromatography are of two general types: packed columns or capillary columns. For most current applications, packed columns have been replaced by more efficient and faster capillary columns. For samples with broad boiling range, it is often desirable to use temperature programming, whereby the column temperature is increased either continuously or in steps as the separation proceeds.
last but not least is the chromatographic detectors. In choosing chromatographic detectors, you must consider the following characteristics. First, adequate sensitivity. Second, visibility and reproducibility. Next, a linear response to solutes that extends over several orders of magnitude. Fourth, temperature range from room temperature to at least 400 degrees Celsius. Fifth, short response time that is independent in the flow rate. Six, high reliability and ease of use. Seven, similarity in response towards all solutes or alternatively a high predictable and selective response toward one or more classes of solutes. Eight, non-destructive of sample. Since we already know the different instruments used in gas chromatography, let us now continue with the different types of detectors used in gas chromatography. The first one is a flame ionization detector. It is the most widely and generally applicable detector for gas chromatography. The most applicable sample for this type of detector are hydrocarbons. The next type of detector is a thermal conductivity detector, a technique used to analyze inorganic gases such as argon, nitrogen, hydrogen, carbon dioxide, and small hydrocarbon molecules. The next type of detector is an electron capture detector, or GCECD, is a technique used to analyze halogenated compounds and is primarily used in the environmental forensic and pharmaceutical markets. The next type of detector is a mass spectrometry detector, which is one of the most powerful detectors in gas chromatography. The GCMS instrument is made up of two parts. The gas chromatography portion separates the chemical mixture into pulses of pure chemicals, and the mass spectrometer identifies and quantifies the chemicals. Other gas chromatography detectors are the following: the electrolytic conductivity or Hall detector and the photoionization detector. Gas chromatography can also be combined with several other techniques like infrared spectroscopy and NMR spectroscopy to provide the chemist with powerful tools for identifying the components of complex mixtures. These combined techniques are sometimes called hyphenated methods. Here are some applications for gas chromatography. It can be used in many different fields such as pharmaceuticals, cosmetics, and even environmental toxins. Since the samples have to be volatile, human breath, blood, saliva, and other secretions containing large amounts of organic volatiles can be easily analyzed using gas chromatography. Knowing the amount of which compound is in a given sample gives us a huge advantage in studying the effects of human health and of environment as well. Air samples can be analyzed using gas chromatography also. Most of the time, air quality control units use gas chromatography coupled with FID in order to determine the components of a given air sample, although other detectors are useful as well. Flame ionization detector is the most appropriate because of its sensitivity and resolution, and also because it can detect very small molecules as well. And for gas chromatography teamed with mass spectrometry, it is also another useful method which can determine the components of a given mixture using the retention times and the abundance of the sample. This method can be applied to many pharmaceutical applications such as identifying the amount of chemicals in drugs. Moreover, cosmetic manufacturers also use this method to effectively measure how much of each chemical is used for their products.
So that's all for today's lesson. Thank you for tuning in. See you in the next one. Bye!